Hey guys, today I'm going to be speaking about complex numbers. In the previous video I mentioned that the understanding of complex numbers was essential for understanding the Riemann-Zeta function. So today I'm going to explain them. Complex numbers are very popular. You'll see them used solving various functions you can't solve in the domain of real numbers. What are real numbers? Let's have a look at that. So real numbers, I'm sure you've met them before. They're all numbers from, they're all the negative numbers, so -1. They can also be -1.456. So they don't have to be whole. Another property is they can be irrational, so like square root of 2, Euler's number, pi, really any number. Now let's have a look at imaginary numbers. These numbers they have a very funny name, imaginary numbers. They're very real. In many experiments, the results of many real world experiments are imaginary numbers. A lot of functions cannot have any solutions without them. They're used in the Riemann-Zeta function. They're also used to solve some integrals. So they're very important, especially in electromagnetism. Okay, imaginary numbers. So the base unit is I, that's the imaginary number. I times I equals I squared. This is all made up, and I squared is basically -1. We've just assigned a value to a letter squared. Now, why do we do that? What's the point of doing that? So if I graph my function f of x equals x squared plus 1, and if I set x squared plus 1 equal to 0, when will my function cross the x-axis? Well, if x belongs to the real numbers, never. Because x squared equals -1. This is a basic algebraic manipulation. X equals the square root of -1. Now, as we know, the square root of a, let's say that a belongs to real numbers, has to be greater or equal to 0. Now, what happens when a is smaller than 0? This is where the trick comes in. We use an imaginary number. See, I squared is defined as -1. So x equals the square root of -1, and if I times it by I squared, basically this will turn into +1, because so the statement was negative, and for it to be still negative, I can't have two negatives. I have to have a plus and a negative. So I squared is the negative. I squared is basically -1 times square root of 1, which is 1. So the solution is plus or minus I, the absolute value of I, because we used the square roots. So the solution to this in real numbers, there is none, but the solution to this function in complex numbers, you could imagine it as extending this function, and sort of this would be the 2 points of intersection on the x-axis in the complex number plane. So imagine another, let's call it a z-axis coming out from the screen, and that's where it would intersect our x-axis. So how do we picture this complex number plane? Well, quite easily, really. So imagine a regular number plane. You've got your 0 here, You got your 1s and your 2s, your 3, your favorite number, which is definitely pi, -1, -2, -3. And all we're doing is we're just adding another number line. Now, this is the imaginary number line, and this is the real number line. So this is all the numbers you're familiar with. This is where, imagine this could be your y-axis basically. And all we're doing is we're putting values like I or 2i, and basically just we're multiplying I by some whole or real number. It can be whole, it can be real, it's really up to you. Actually, it needs to be whole, sorry. This is minus I, this is minus 2i, and so on. Now, what you'll notice probably is that some things start to repeat. So if I equals I and I squared equals I times I, and that equals -1, then what does I to the third power look like? It's I squared times I, which is basically, if this is -1, -1 times I is -I. So I to the fourth power is I squared times I squared, which is basically -1 times -1, which is 1. I've still got some space below that. I to the fifth is basically I to the fourth times I, which is basically I. And as you see, it's getting repeated. I to the sixth power is I to the fourth times I to the squared. So as we saw, that I to the fourth is 1. So 1 times -1, I to the sixth is -1, and we're just really going in circles now. So if we graph that so that it makes more sense, what you're doing essentially is you're just really going in a circle and you're having the same I values returned. Now, a complex number has a defined structure. Let me find you a different color. So this is the structure of a complex number. That's how it looks like. So this is the real part, and this is the imaginary part. B belongs to whole numbers, and A can be any real number you want. So 0.2, 0.3 is really up to you. But this needs to be a whole number because we don't know what 0.2i is really. Now, how does this look like? This is I, and this is -I, and this is A. Then A plus 1 times I, so 1 is the B, is this point. You could also graph it as a vector. And what happens when this is negative? So A minus 1 times I is this point. Another important thing to mention, Z means complex number. You'll see this notation used everywhere, and all it means is A plus BI. Z with a hat on it or a line is basically A minus BI, and Z in the absolute value means what you're doing is you're putting everything under a square root and you're giving it an exponential value of 2. And you're just really calculating the length of your vector.